of x, and it's just equal to pi of x plus 1/2 pi of x to the 1/2 plus 1/3 pi of x to the 1/3, and so forth. It's just the sum, or pi of x to the 1 over n over n, where 1 over 1 is understood to just be pi of x. So yeah, so Riemann defined this sum, and what he by defining this guy, and then doing the same thing, taking the logarithm of the zeta function, he was able to simplify this to a much more workable form. This is so he did the exact same log of zeta in terms of this guy, and this is what he got. So he defined this j function, which I showed you guys, and if you see, this j function actually is not an infinite sum, because for every number, there's a certain number. If you take enough roots of that number, this thing will be less than 2, and pi of that number is 0. So this is not an infinite sum. He will cut it, no matter how big the number is, he will cut off eventually. So yeah, so he noticed this j of x, he defined this j of x, and was able to get this guy. It's much easier, so it's exactly this, what we see right here, just in terms of this j function. And now but having it look like this, Riemann said, "Oh my God, this is great." He was a master of Fourier analysis, so he said immediately, he saw that, and he's like, "Oh, I'm just going to invert the relationship." This, we'll come back to this. It's he knows the applicability of the Mellin inversion theorem. It's just a inverse Fourier transform to invert the relationship. You have, and I'll talk more about this later because you will need it later. But if you have this guy, actually, I'm gonna bring this s down here, and so if I have this guy in terms of some integral of something to the x to this power, I can write this guy like this in terms of an integral through the complex plane of this guy to some power. And this is a Mellin inversion theorem. This is named after some Finnish mathematician, Mellin or whatever, but Riemann's work predates that of Mellin by 40 or 50 or 60 years. It was quite incredible. Alright, so yeah, so whatever. So I'll get back to the Mellin inversion theorem later. I would love if we can get to stuff like this in your class next semester. I would love to see the proof. I would love to see the proof of theorems like this. I would love. What's it called? So yeah. So he just he inverts this relationship. And then this, if we have time at the end, I'll show you guys what he did on here. Basically, all he did was he found another expression for log of zeta, substituted it into this guy, and then just integrated term by term, and eventually ended up with this. Where, of course, you could have seen it coming. The first term is that logarithmic integral, minus this guy, and minus these two guys. Now, I'm going to talk about these two guys in a second. Here, this sum right here runs over rho, where rho is the non-trivial zeros of the zeta function. So, yeah. There's a long presentation. We're going to get to it. Right. So just to keep going, so yeah. So this is the formula he got for j of x using the Mobius inversion, which is another type of additive inversion thing. You could go back from j of x to pi of x. So then he just put this formula into this thing, and you were able to invert, you're able to go back from j of x to pi of x. And so basically what he got, this was his approximation, which basically says that, it's just taking the logarithmic integral of x minus 1/2 of this guy, minus 1/3 of this guy, plus minus this, plus 1/6 of this guy. Basically, if the number n right here is an odd number of prime numbers, then it's a minus. 6 is 2 times 3. Since it's even amount of prime numbers, it gets a plus sign. And it keeps going. So, there's the Mobius function, which Henry knows a lot about. What's it called? So yeah, so putting that back into here, he goes back to pi of x. And so, but the main thing though, here was out of this formula, this is just an exact this is just an approximation. Here you can see, Riemann's error compared to Gauss's error. It's considerably better, but there's still an error term. And none of this is important. The main part is this part. It's the importance is he was able to give an exact analytic formula for the error term. That error we've been looking at this whole time, it's right here. Remember, it's right here where this row goes over the zeros of the zeta function. These are the two lesser terms. I'm calling them the lesser terms because why? Because a log of 2 is a measly little 0.69. And then this guy, it's the integral from x to infinity. He's always going to be less than or equal to 2 to infinity. And this guy is just 0.14. And for all x greater than 2, so the biggest he gets is at 2. And then as you bring x greater, he gets smaller and smaller. So that's why we even call them the lesser terms. They add very little error. The majority, so 99% of this error is all right here. It's all these zeros of the Riemann zeta function. The lesser terms barely contribute anything. So now we're going to talk about the zeros, the trivial, the non-trivial zeros. Riemann's approximation improved on Gauss's approximation, as we can see right here. There's actually even terms. There's terms that asymptotically give you a difference of 0. Like it's the thing is so when you round it off like this, it's 0. But it still fluctuates a little bit here and there. It's all the zeros of the zeta function. So yeah. So the importance of Riemann's work was that exact analytic formula for the error. It explicitly states that the non-trivial zeros of the zeta function control the error term as a prime number theory, which is the guy that it's just that pi of x is about logarithmic integral of x, and the error of that is directly controlled by the zeros of the zeta function. Yeah, this seemingly esoteric condition is of fundamental importance in the distribution of the prime numbers. In other words, this is where the Riemann hypothesis becomes very important. The Riemann hypothesis is equivalent to the best possible bound on this pi of x minus logarithmic integral of x. It pretty much gives order to the prime numbers. It will say that they're distributed randomly, but in the nicest way possible, more or less. So here it is, the Riemann hypothesis, 18, and said, oh, this, not only would it be elegant, not only would it be awesome if they're all there, but it would also do all this. It would give you the best possible bound. So he said, hey, why not, let's just hope they're all on this one half line. This is my conjecture, that they're all there because, like nature, you would think it wouldn't have like these weird things, You'd like to see nature like as nice as possible. All right. Hey, we're gonna come back to this. I don't even know why I put this right here, but it's just from this definition of the zeta function, we can see that the zeta function has no zeros in the half plane. So here's the complex plane. Here's 1. All throughout here, we know from this half plane forward, we know that the zeta function has no zeros because the zeta function can be expressed like this in that half plane, and none of these terms is ever 0. So here you have an infinite product of a bunch of guys that are not 0, therefore the whole thing is never 0. So that's pretty nice, but alright, now we're going to have to get down to business. Before we say more about the zeros, we need to develop this theory and the zeta function a little more in depth. Well, first, let me introduce the gamma function. Euler was the first to extend. The gamma function is just an extension of the factorial function. Today, this is basically going to be an introduction to special functions, all types. You're going to see the gamma function, the Jacobi theta function, whatever, zeta. You're going to see a lot of guys. So the gamma function is just an extension of the factorial function. Euler, in the 1700s, he noticed this simple integral. If you keep integrating him by parts, by this guy, using this guy as your u, take the derivative, you get n t to the n minus 1, right? Keep doing that, n minus 1, n minus 2, blah, blah, blah. And this guy is exactly, for s equal to n, for s equal to a natural number, this guy gives you exactly the factorial function. So you can think of this as a generalization of the factorial function, you know. Now, so yeah, Riemann defined some big pi function, but that notation didn't stick, the capital pi function. Legendre was the guy who introduced this notation, using this little gamma thing. What's it called? And this is the exact definition of the gamma function.
Who introduced pi?
Legendre. I don't know.
It's gamma. Who introduced pi?
Riemann. No, actually no, Gauss. Gauss had already introduced it. Riemann studied under Gauss, so he used it. But the thing is, this notation had already stuck in France. I say right here that I guess Legendre's reasons for considering, because the thing is, this guy is equivalent to n minus 1 factorial, whereas this big pi function would be equal to that integral. So instead of just changing this s minus 1 to just s or just n, it changes it from n minus 1 factorial to n factorial. What's called this? Legendre introduced this notation and it just stuck. In France, everybody was using it. So I mean, and yeah, it's weird. I don't know why you consider n minus 1 factorial instead of n factorial. I guess it's because he felt it was more natural to have the first pole occur at s equals 0 than at s equals negative 1. And the motivation for this function is just a function such that f of x plus 1 equals x f of x. And this is the exact functional equation for the gamma function. The gamma function was extended to all real numbers except the negative 0 and the negative negative integer, where it has simple poles. Which you know what we were talking about. It has the simple poles at the negative integers. That's when you put, you know, if you put s at s equals 0 is the first pole. It's t to the negative 1 over there, and then just any negative integer will give you a pole of this guy. This is going to be important later for the trivial zeros, and those are the guys we don't care about. But whatever. Alright, so the gamma function satisfies these well-known functional equations. They're valid for all s. We've seen this one already. And then these are some other ones that are valid for all s also. Here, there's the thing connecting them to the square root of pi. We have this pretty famous constant that gamma of 1/2 is the square root of pi. Just like, you know, anybody ever thought, hey, what's 1/2 factorial? What's 1.5 or 1.7 factorial? You can't really do it just multiplying integers, but using the gamma function we can do it. And you get that between integer values, you get terms in terms of the square root of pi. And now I need to introduce also the Jacobi theta function. This is just, we're going to use this guy a lot right now. It's just this infinite sum. It looks weird, from n equals negative infinity to infinity. So he comes from this way, all the way from negative infinity this way, to negative 2, to negative 1, to 0, that it gives me 1, to 1, to 4, to 9, and so forth. And Jacob also do to Jacobi this functional equation. If you put in x, you get the same value of x, you get it as putting 1 over x into this function and dividing by the square root of x. You get it's a functional equation, just like this, that's valid for all x. Yeah, this is one of the Jacobi theta functions. Pretty important, like in analysis and stuff. So yeah, so we're going to need this theta function too. So now, the functional equation, and this is one of the main parts of today's lecture, is the functional equation for the zeta function, is the relationship between zeta of s and zeta of 1 minus s. So if you have, this is where I may have to bring this up. If you know what the function, what zeta of s is, using this functional equation, you can relate it to a value of zeta of 1 minus s. Now, here we're going to derive the functional equation in terms of its symmetric form. It's really the nicest, and it'll also prove to be the most useful a little later on, which is like this. It's just, you see here, it's exactly the same, but the only thing changes from s to 1 minus s. So here, this version is called the symmetric form, and whatever exactly is going to prove to be pretty useful. And this is what we're going to need in order to derive this functional equation. We're going to need the gamma function, which we just introduced, the theta function, and this functional equation.